Yes, I would like to thank the organizers for the kind invitation to this conference. And I would also like to acknowledge the hospitality of Beijing Normal University, where I have spent some time before the conference. The topic of my lecture is to report on the progress in studying F-theory compactifications. And so this will be the focus of my lecture in the outline that may end up being summary in the case I run out of time. I will briefly overview the key ingredients of non-abelian gauge symmetries and then proceed toward a discussion of progress on abelian gauge symmetries, which are related to rational sections of F-theory compactification and their connection to Mordell-Weil group. And I will also highlight insights we gain into heterotic duality with abelian gauge symmetries. Then I'll proceed with discussion of the progress of discrete gauge symmetries in F-theory, their connection to multi-sections in F-theory compactification, and relationship to Tate-Shafarevich group. Again, here I'll highlight recent work on heterotic duality and the role of mirror symmetry to address origin of discrete symmetries there. I probably won't have any time, but I would still like to mention that all those techniques have been applied to constructions of global particle physics models. And in recent years or so, we didn't only make progress with grand unified models, but also with construction of a standard model and working progress on a standard model with Z2 symmetry R parity. The emphasis that I'm going to make will be on geometric perspective. And while this can be viewed in part as an overview of F-theory compactification, I have to apologize because it's going to be UPenn-centric. Before I proceed, let me highlight actually the work that I'm going to, some aspects that I'm going to present for heterotic F-theory compactification and the role of abelian and discrete symmetries was recently done in collaboration with Antonella Grassi and Maximilian Porechkin, as well as with Dennis Clevers and Peng Song. So the key ingredients in F-theory compactification are based on fiber Calabi-Yau manifolds where the torus modular parameter is associated with complexified gauge coupling of the type 2B gauge theory. The typical representation of such elliptic fibration is in terms of Weierstrass normal form, which is represented as an elliptic curve that is a hypersurface in a weighted projective space P1 to 3. When elliptic fibration degenerates, that signifies the large string coupling and location of non-perturbative branes. In particular, along the divisor in codimension 1, we encounter non-abelian gauge symmetries. At the intersection of two divisors, we encounter matter, and at the triple intersection of divisors, the Yukawa couplings. So let me say one or two more words about non-abelian gauge symmetries. So in particular, along codimension 1 divisor, in Weierstrass normal form representation, the singularity is signified by the order of vanishing of F and G terms as well as their discriminant. After resolving this singularity, we end up with a structure of P's over this divisor, and the structure is in one-to-one correspondence with the corresponding non-abelian Dynkin diagram that signifies the origin of non-abelian gauge symmetry. Specifically, the Cartan gauge bosons via M-theory duality are supported by 1,1 forms on resolved Calabi-Yau that is in one-to-one, those forms are in one-to-one correspondence with the corresponding P1s in the resolution of this codimension 1 singularity. Now let me turn to abelian gauge symmetries. For abelian gauge symmetries, we need a 1,1 form that supports U1 gauge boson, but it's associated with an isolated I1 fiber because we don't want to enhance this symmetry to a non-abelian one. It was derived a long time ago that those isolated 1,1 form that support U1 gauge bosons are in one-to-one correspondence with the rational section of elliptic fibrations of Calabi-Yau manifold. Now, rational sections of elliptic fibrations, of course, signify rational points of the corresponding elliptic curve. And in particular, for the case of elliptic curve, we have always a distinct 0 point. Now, if elliptic curve is of a special type, to have additional rational section, it would correspond to a rational solution in field K of Weierstrass form. And this set of new rational points as solutions of Weierstrass form turn out to form a group under addition, the so-called Mordell-Weil group of rational points. Now, the rational point clearly induces a rational section of the elliptic fibration, and this rational section gives a second copy of the base, namely the new divisor in the Calabi-Yau manifold. This divisor is a horizontal, non-local, and completely non-singular. The way one constructs the corresponding 1,1,1 form is precisely from this non-singular divisor via the so-called Schuda map and obtain the corresponding 1,1 form that supports the abelian gauge symmetry. Thus, those forms are indeed in one-to-one correspondence with the rational sections. Now, what we need to construct for compactification with additional U1s is indeed starting with the elliptic curves that have more than just 0 section, that have additional 0 point, but also additional rational sections. And those additional rational points on elliptic curves can be constructed via bundle construction on specific elliptic curve, which results in a specific curve that is a Calabi-Yau hypersurface, typically in a blow-up of weighted projective space. So this approach was recently initiated in the work of Morrison and Park, who systematically constructed additional rational point on elliptic curve on a generic Calabi-Yau that is a hypersurface in blow-up of P112. A lot of work was subsequently done on constructing compactifications with 2 additional rational sections with specific examples corresponding to curves which are Calabi-Yau, generic Calabi-Yaus in DP2s, and some recent generalization that are results of non-generic cubic in P2. One actually proceeded with the systematic approach all the way down to 3 additional rational sections, but it turns out that beyond that, things seem to be much harder, and it's not clear how to systematically proceed with this program. So let me turn now in this context to pointing out some features of this generalization of constructions with 2 rational points, which is a non-generic cubic and P2. So this particular elliptic curve is parameterized as, by specific cubic in P2, where coefficients AI and BI actually determine the location of 0 and 2 additional rational sections. So as we vary those coefficients, we can move the rational points on the elliptic curve allow them to collide, and study actually under collision the non-abelian enhancement of original abelian gauge symmetries by merging those points. So in particular, one can address how these non-local horizontal divisors associated with abelian gauge symmetries turn into local vertical divisors of non-abelian gauge ones. And one has demonstrated this phenomenon in this context, both in geometry as well as in field theory, by specifically identifying the matter fields and their representation that allow us to unhex this abelian gauge symmetry to examples of non-abelian ones. In particular, that led us also to first construction of symmetric representations of SO3, that also led to further effort in general to construct higher index representations in F-theory compactification. Now, I promised I'll highlight some aspects of heterotic F-theory duality within U1. And so for this particular case, we have to focus on the origin of heterotic F-theory duality in the most basic way. Heterotic E8 cross E8 string theory on two torus is dual to F-theory compactify on elliptically fiber K3 surface X. If we want to see this basic duality in a manifest way, we go to the so-called stable degeneration limit. We fiber the elliptically fibered K3 surface over specific P1 that specifies specific moduli, and at particular point in moduli space, the K3 splits into two half K3 surfaces. And the dictionary that relates data of this half K3 surfaces to the heterotic data is the following. The half K3 surfaces contain information on the background bundles V1 and V2 of the heterotic string theory. Heterotic gauge group is the commutant of the structure group of the corresponding background bundles. And the heterotic geometry, the elliptic curve, appears at the intersection of those two half K3 surfaces. So what we want to study is specifically by employing toric geometry techniques to study stable degeneration limit for models with 1U1. So those are Morrison-Park type models, where the elliptic fibration is specified by a curve that is a hypersurface in the blow-up of P112. So we employ the toric data, in particular the toric polytopes that specify the data of this geometry, and also the dual polytopes, the so-called Newton polytopes that again further specify the elements of the monomials in this hyperplane constraints. Now, when we focus on the dual Newton polytope, we turn to the decomposition of F-theory geometry in the stable degeneration limit, and it turns out that this geometric structure is very suggestive, with the top and lower layer corresponding to data on the so-called spectral cover of the heterotic dual, and the middle sector corresponds to the elliptic curve of the heterotic dual. For specific cases, we wanted to study the SUN bundles, and that's why the spectral cover data that we read off from after stable degeneration, and also we didn't want to have too large bundles, so we specialized this data in such a way that we ended up with a large heterotic dual gauge groups. In any case, within this context, I want to highlight a new point that was not an issue when one was dealing with just non-abelian gauge symmetries. Namely, we study K3 surfaces where fiber is specified by P112 and take its stable degeneration limit to two half K3 surfaces with fibers again specified by P112. But we can also take another route by mapping this K3 surface specified by P112 into the Weierstrass normal form and then take a stable degeneration limit. It's the first round that we took, but as I said, one could think of taking this route. It turns out that actually those two routes do not commute, and it's only the left one that produces the right heterotic data for us under stable degeneration. Okay, so time is ticking, so let me just highlight some of the specific results, how we trace U1 through heterotic duality. So a particular case now that we have is a case where in F-theory we have an additional rational sections for additional U1. And what we want to focus on is what happens to this rational section, in particular going across the heterotic elliptic curve. And it's this data that signifies for us the origin of the heterotic dual U1 symmetries. So the case that I'm pointing out here is the case that actually with this rational section in stable degeneration continuously goes across an elliptic curve. Nothing special happens to it. And those turn out to be examples with spectral cover whose bundles are split bundles with an extra U1s. This is a simple example, so we have two split bundles in each of the half K3s. The corresponding gauge group has also two U1s. However, in 6 dimensions, those two U1s are massive due to background U1 bundles, and only a symmetric combination of these two massive U1s survives as massless U1, and that's this massless U1 that corresponds to the massless U1 in the F-theory. We also can have situation when the rational section, additional rational, precisely merges with the zero section. And in this case, the bundles end up being split bundles with a torsion. The corresponding U1s remains massless also in the U1, and it's the one that we match onto F-theory. We also have a case 3 with the split SU cross SU bundles. So in the last 10 minutes, let me focus on progress on understanding discrete symmetries in F-theory. The appearance of discrete symmetry in F-theory is associated with Calabi-Yau geometries that are not elliptically fibered but are genus 1 fibrations. So those are geometries that do not admit a section but a multi-section. While earlier work was done in the 2000s, there was extensive, intense efforts just 2 years ago to address the origin of this discrete symmetry in F-theory some more. And let me very briefly just highlight 2 key features. One is actually observation that models with U1 symmetries are related to models with discrete symmetries via so-called conival transitions. And another one is that geometries with n sections, namely those with discrete symmetries, are in one-to-one correspondence with the Teixeira-Farevich group. And while most of the work was done on Z2 along those directions, it's actually Z3 that brings some new subtleties in this interpretation and was pursued by work at Penn. So connection of constructions with U1 gauge symmetries to those with discrete symmetries is geometrically associated with appearance of co-dimension 2 singularities in the fiber where those additional sections collapse. Okay. So the zero section and additional sections all collapse at this co-dimension 2 singularity, and pursuing then the formation, namely gluing in a 3-sphere, results in regular geometry, but this geometry does not have sections anymore. The original multiple sections became a single n section. We see that phenomenon also in field theory, namely co-dimension 2 singularity always signifies appearance of massless matter. In this case, it would be massless matter with charge 2. And in the new phase, this matter acquires vacuum expectation value and breaks the original U1 gauge symmetry to discrete Z2 symmetry. So this interpretation, both geometric and field theoretical has been also pursued for constructions of U1 geometries with matter charges that have higher n value, in particular for n equal 3, including effort at Penn. But I don't have time to go into that. However, I can help myself to highlight a new subtlety that one encountered when studying, trying to interpret the origin of Tate-Shafarevich group in the case of Z3 symmetry. Okay. The puzzle had to do with the fact that when we are dealing with geometry that has a trisection, there's only one geometry, okay? And another element in the geometry is its corresponding Jacobian map. Nevertheless, it turns out that the Jacobian action on trisection geometry and its inverse section produce different elements of the corresponding Tate-Shafarevich group, and this actually produces for us 3 different building blocks necessary to confirm relationship between geometries with trisections and the corresponding Z3 symmetry of the Tate-Shafarevich group. So in the last 5 minutes or so, let me highlight also some of the insights on discrete symmetries that we obtained by studying heterotic F-theory duality. And in particular, we wanted to trace the origin of discrete symmetries on the heterotic side of this duality. So for that purpose, we employed the following conjecture by Berklund and Meyer, who in the Weierstrass example observed that if we start with the toric K3 that in the stable degeneration limit has singularities in each half K3 associated with G1 and G2 symmetry group, okay, the corresponding toric dual would be the one that would have singularities in each half K3 that are commutant of the original G1 and G2 singularities. So basically, the original K3 and its dual K3 exchange the origin of gauge symmetry and the corresponding structure group of the vector bundles. And it's this duality that we explore to really study now, starting with the construction of background bundles that have a structure group whose commutant is now the discrete symmetry. So more specifically, we also looked only at examples that are symmetric. And in this analysis, we go beyond basically the basic Weierstrass map. So an example of Z2 symmetry would be starting with the actually Newton polytope of that type. Is just the upper half, but we have the symmetric structure that results in a gauge symmetry that is E7 cross SU2 in each half. Now, if we construct a dual polytope and view that as a Newton polytope of a dual theory, we end up with a gauge symmetry, namely that is now only Z2. So namely the bundle here becomes gauge symmetry here, gauge symmetry bundle here becomes gauge symmetry on the left. Now there is actually a subtlety as we go from 8 to 6 dimensions, because we don't expect this doubling of the gauge symmetry to be there, that there is really only the single Z2 gauge symmetry as it appears in the F-theory limit. The way we can understand that is actually via field theory, by going back to the example I showed earlier, namely the example with symmetric 2U1s, which in 6 dimensions were massive and only one linear symmetric combination was massless. So Hicksing such a model would now result for us really only in a single Z2 that is a manifest, so-called massless in quotation mark, symmetry that survives. So actually the massive U1s come here also in this field theory interpretation of the Z2 gauge symmetry in this dual example. We identified the same phenomenon also for the case of geometries that result in a Z3 gauge symmetry. And I should also emphasize an intriguing observation that actually all these examples are examples where we start with Calabi-Yau construction that has Mordell-Weil torsion of order n. And via heterotic duality, we relate them now to dual toric Calabi-Yaus that have an n section and discrete symmetry. And so this relationship via heterotic duality between Mordell-Weil torsion construction of order n and constructions with n sections becomes manifest, really. Though one would like to prove it in more general context, not via the step of heterotic duality directly in F-theory. So I still have a minute or two. I thought I will run out of it, so maybe I should still highlight how some of this progress in F-theory compactification, both for abelian and discrete symmetries, has been applied to construction of particle physics models in F-theory. The story about particle physics construction is by now 8 years old and was primarily focused on SU5 granifications, leading both to local and global models. But in recent years, one also pursued direct construction with building blocks that would give us directly the standard model, and actually resulted to global examples of three-family standard models and other particle physics models, as well as work in progress where we would like to implement construction of a standard model with Z2 symmetry that would act as an R parity, very important part of in an attempt to connect F-theory constructions to semi-realistic particle physics. But I'm really out of time, and I would really just like to highlight the standard three-family standard model construction. Again, toric techniques. Elliptic curve is a hypersurface in DP4. The codimension 1 singularities result in SU3 cross SU2, and then there is an additional section resulting in U1. We can identify matter representation in this construction, precisely the building blocks of the chiral matter of the standard model. To get the chirality, we also have to include G4 flux, borrow from F-theory duality, and satisfy global conditions. And just taking an elliptic fibrations where the base is very simple, just P3, allows us to construct such models now with, that are actually completely specified just by multiples of hyperplane divisors, and 7 and 8. They allow us to construct specific Calabi-Yau, elliptically fiber Calabi-Yau spaces, and then by turning on fluxes, we have to satisfy both the global conditions and identify the number of families. And in this class of allowed models, we indeed have models that have 3 families and positive integer number of D3 branes. The phenomenology is not great, and that's why we are also building the model with a R parity, Z2 symmetry, again, connection to constructions with genus 1 fibrations. So let me conclude. So I guess I can still flash this. So I try to spell for you key ingredients for F-theory compactification and emphasize the geometric perspective where we really can get a handle on discrete data, namely on the origin of gauge symmetries, representation of matter, and possibly determine the Yukawa couplings. And then I focused really more on progress, more formal progress on construction of models with abelian gauge symmetries, as well as discrete symmetries, and the relationship to Mordell-Weil and Teichafarevich group. And I highlighted some insights into heterotic duality with those types of symmetries. Didn't say much, but that's also another major part of my interest is really global particle physics models, and highlighted just one example of 3 family standard model. I believe this is just the tip of the iceberg. After all, we got that just with the simplest possible base of P3. There are really crucial issues that we cannot handle yet well, namely detailed continuous data such as magnitudes of couplings. More has to be addressed in terms of moduli stabilization, much more work to do, and thank you.
Is there any questions? Well, since there are no more questions, let's thank